Hi guys, welcome back to Calculus. Today we're going to talk about average and instantaneous rates of change. But what are the difference of the two? Well, let's think about a road trip that you took recently. Maybe you drove to your grandparents' house, maybe you drove on vacation, maybe you drove to the mall. But just think about one of the last trips that you took in your car. And let's talk about your path. So, when you drove in your car, or when your parents drove, or whoever was driving, they probably did not drive at the same speed the entire time. They probably had to stop at a stop sign or a stoplight. They probably had to speed up at some points. Maybe they slowed down. Maybe they parked. Maybe you had to stop and get gas. But overall, we can take all those variables into consideration and calculate the average rate of change. And that would just be by taking the total amount traveled, so the total distance, get rid of these adds, total distance, and divide that by the total time. So the average rate of change kind of thinks, okay, well, how far did you go and how long did it take you to get there? So if you traveled 100 miles in 2 hours, then your average rate of change would be 50 miles per hour. Now, granted, you probably didn't drive 50 miles per hour the entire time. There are times that you were speeding up, times that you were slowing down, maybe even times that you were stopped. But on average, your entire trip, the average speed that you went was 50 miles per hour. Instantaneous rate of change is exactly what it says. It's an instant rate of change. So what that asks when you answer a question with instantaneous rate of change is how fast were you traveling at a specific time? So maybe like at, I don't know, maybe 11 or 10, 17 a.m. and 35 seconds. So an instantaneous rate of change is at a single instant, how fast were you going? Now, you probably have not calculated instantaneous rate of change, because to calculate that, you're going to need some calculus, and that's a skill we're going to do today. But you probably have calculated the average rate of change today. So the problems you're going to do today deal with how we calculate average rate of change mathematically and how we can use the average rate of change to help us estimate an instantaneous rate of change. And eventually we'll be able to calculate it a lot faster. But today we're going to start with average rate, move on to instantaneous rate. So the math of the lesson is going to be all about lines and their slopes, which I know is not as exciting as a Tesla, but we need to know the math and the numbers behind all of that stuff. So one question you're going to be asked, what is a secant line? Then what is a tangent line? And then how do we calculate the slopes of each? So you can find these notes in your notes packet on page 7. We'll be going on page 7 and then flip forward a page. But if you have a graph and you connect the graph with a line, and that line hits the graph in 2 points, we call that line a secant line through points P and K, and that's called the average rate of change. And we've calculated the average rate of change in the past by calculating the slope. So you'll see this notation, M subscript SEC, meaning the slope of the secant line, we can calculate as the change in y divided by the change in x, or the formula for that, y2 minus y1 over x2 minus x1. Slope. You've seen it probably 500 times at this point. Well, if you draw a line and it only hits the curve in 1 point, we call that a tangent line. And the slope of the tangent line is how we get the instantaneous rate of change. So we'll see the notation M subscript TAN, which is referring to the slope of the tangent line. And how are we going to calculate this? We don't know yet, because this is new. So to calculate the slope of the tangent line, we're going to start with the slope of the secant line, and we will work our way to how you calculate the slope of a tangent line. So let me show you how Delta Math is going to ask you about the slopes of the secant line. So we have an example pulled straight from your homework assignment. It says the function y equals f of x is graphed below. Plot a line segment connecting the points on f where x equals -3 and where x equals -1. So plotting that line right there. Done. Use the segment to determine the average rate of change, and remember, average rate of change is slope, on the interval from x equals -3 to x equals -1. So then we're asked the change in y, so the difference in the y value. So -5 and 25. So the difference y2 minus y1 would be 25 minus 5. Looks like that would be 20. And then the change in x, the difference in the x's from -3 to -1. Looks like that would be, the difference in those would be 2. And I'm missing a negative somewhere. So let me label these points. So this is the point -3, -5. And this is the point -1, -20. So if I want to do my slope, I'll do y2 minus y1, -20 minus -5. No, that's not -20, that's -25. All over -1 minus -3. So -25 minus -5 is -20. -1 minus -3 is like -1 plus +3, which is 2. And -20, so I change this, -20. -20 divided by 2 would be -10. Now flip backwards a page in your notes, in your packet, and you'll end up at page 3 in your notes packet. Let's talk about tangent lines for a minute, because I know you've heard the word tangent from geometry, and maybe you talked about lines being tangent to a circle. So you would say that a line is tangent to a circle if it intersects the circle at one point. In the figure to the left, the line is tangent to the circle at point P. But this definition where we say if it intersects at one point, it's not the best definition, because tangent lines can be a little more complicated. So I'm going to show you some examples and non-examples of tangent lines. But and it's hard to come up with a definition at this point in your math life, but a line is tangent to a curve if, and here's a rough definition, if it follows the path of the curve. And hits the curve or intersects the curve at one point on a portion of the graph. So, for example, the first picture right here, it's labeled a misconception, because if we just define a tangent as being a line that hits the curve in one point, then I could draw this line this way, hit it once, and it's still not a tangent line because it's not really following the path of the curve. So let me grab a line and show you what I mean. So you see how the curve is kind of going downwards? We want our tangent line to pretty much show the slope of the curve at a specific point. So we draw, and it's hard to, you can't really find a slope of a curve, but we can draw a line and find the slope of the line. So if I draw a line that hits it right there, and I can adjust my line a little bit. Let's adjust it so that it hits it at one point, So this is more of a tangent line because it's showing that the curve at this section of the graph goes downward, it decreases. So I have my slope is negative and it follows the curve a little better. The second misconception is that a tangent line can only hit the curve once. That's not true. This line right here is definitely a tangent line and it hits the curve 3 times, but it's a tangent line because we're only focused on this section, this section right here of the graph. So I'm only looking at this part to see the tangent line part because I only want to worry about the slope of this part of the curve. And then if you do it, lines extend forever and ever in both directions. So if this line does extend forever and ever, it does hit the curve 2 more times, but the line wouldn't be tangent up to the curve at this point. It would only be tangent to the curve at this point. So can you see how, like, if the definition of a tangent line hitting a curve at one point can lead to a few misconceptions? So let's look at a couple examples. Here's let's see. So here's a couple problems, and your notes do not have the graphs drawn, but I've already drawn the graphs. So if you do want to pause the video and copy the graphs on to your notes, that would be a great idea. So we're going to sketch a tangent line at each indicated x value. So this wants me to sketch the tangent line at x equals -1. So I look at where x equals -1, which means I'm interested in drawing a tangent line at that point. And tangent lines follow the path of a curve. Well, this line is not a curve, it's a line. So if I want to show the slope of the curve at this line, at this point, this one's going to be kind of weird, but really all I'm going to do is I'm going to draw a line. Oops, I need a line. I'm going to draw a line on the curve at that point. Now, if I put the line right here, yeah, the line hits the graph in one point, but it's not showing the slope of this line. So the slope of the tangent line should really just match up with the same line. So the slope of the tangent line in green ends up being the same as a line. So when you're drawing a line and you have a tangent line, they end up being the same line. So when you have a line, its tangent line will be the same point, will be the same line. Okay. The second example, I need to draw a tangent line at x equals 0. So x equals 0 is right here. So at this point, I want to draw a tangent line. I want to show the slope of the curve at this point. So I'm going to draw a line. Let's see, if I draw it like this, it does, if I try to draw it diagonally, you see how it's hitting the curve here and then it hits it again. It's not really showing that my curve is flat at that point. So at my parabola, my tangent line ends up being horizontal. So the tangent line at curves, no, not at curves, at maximums or minimums, on smooth curves, by smooth I mean not pointy, the tangent line at maximum and minimums on smooth curves will be horizontal. Now, I know you might be asking yourself questions like, how am I going to do this? How am I going to know? It does take some practice. And the way that your homework questions are asked, I think is a little less stressful. So let me show you how you're going to be asked about that. So you'll be given a graph and you're going to be asked to draw a tangent line at a specific point. So on this graph, it's indicating that I want to do the tangent line at the point x equals 1. So it says move the yellow dot in the upper left corner of the screen in order to make a tangent line given when x equals 1. Okay, so I'm going to drag this around to help my line move until I try to figure out if it's matching the curve. Now I notice that the curve is increasing at this point and the points around it. So I want to make a line that is also increasing and kind of having this same slope. So I'm just going to drag it around, try to follow the path of curve as close as I can. Now it asks you to zoom in, and the reason it asks you to zoom in is because it wants you to see if when you zoom in, if it looks more like a tangent line. I think, oh, maybe I should adjust this a little bit more. And then when I zoom out, I want to make sure I'm not drawing a secant line. So I zoom in, maybe adjust it a little bit more to follow the path of the curve. And notice when you zoom in, it looks like a line almost. So you want to try to get it to match that line where it is. Then I'll submit my answer. There we go.